Spacetime. What is it? Let's start off with space. Our universe has three spatial dimensions. There's one, there's two dimensions, and then there's three dimensions. You can determine and describe the position of any object just using three coordinates. But if you want to explain motion, or where something was yesterday, backwards in time, forwards in time, you need time, a fourth dimension. And so with now four coordinates, you can describe where an object is in our entire universe at a given time. That's space-time. Now, Albert Einstein linked the two together, space and time, together as one word, space-time, and explaining gravity as the curvature of space-time in relativity. But Einstein was not able to define what was being curved. Now, before Einstein's work on relativity, Max Planck created the Planck unit system, and these units are not based on human constructs, such as the meter or the kilogram, which are things that we can visually see or measure. They are based on the natural units, properties of free space. You can see Planck mass, time, and length down there at the bottom right, and there's much more, but we're going to go over those three. But Planck could not describe why the units are natural and why they simplify physics equations. Now, one more thing on background first before we get into it. All right, to explain issues found by Planck and Einstein, actually a lot more than just that, but Planck's black body radiation, Einstein's photoelectric effect, quantum mechanics was eventually conceived to explain the nature of atoms and its particles. So basically things that are smaller than the atom require quantum mechanics. But of course that creates a brand new issue, which is the objects in space-time follow two different laws under current theory, one based on their size. One is classical mechanics for everything larger than the atom, and then there's quantum for everything smaller than the atom. Two different laws. All right, let's try to break this down and see if we can make sense of it. And so let's apply what Planck found as natural units and put it in space-time. Right, let's put the Planck mass there. And let's define a three-dimensional grid with objects at Planck length. And then what is Planck time? Well, that describes motion. And if you take a Planck length divided by Planck time, you get a speed, and that speed is the speed of light, how fast light moves and electromagnetic waves move. Now let's take it a step further. Let's apply classical mechanics to the granular structure of space-time. This is incredibly small stuff, so yes, this would be in the quantum realm. And we're going to use classical mechanics because really the universe should abide by one set of laws. So let's assume that granules may be displaced from their original position. Granules is the term being referred to something at that Planck level. And it distorts space-time, similar to what Einstein described, but eventually returns to equilibrium, i.e. harmonic motion. Now, why that last part? Because classical mechanics can describe harmonic motion, such as a spring mass system, although I'm not saying that space-time literally has springs, but it can be modeled that way mathematically. So let's break down that grid structure into the smallest parts here called a unit cell. And when something is displaced over time in harmonic motion, you can see that wave, the sine wave structure. And furthermore, the peak amplitude that you see there is going to be shown to be the electrical property of charge. Now, modeling space-time as a spring mass system has a few different advantages. First off, the harmonic motion forms waves that are found in nature. Particles are known to have wave formations, and certainly electromagnetic waves do as well. So waves are found throughout the subatomic realm. Now, the Planck mass shows up, and Planck mass is quite heavy, especially for its small size, if we assume that it's going to be somewhere near the Planck length. But modeling it as a spring mass system, the energy only comes when it is displaced. And so you see that there on the left, no energy if it's not being displaced despite having Planck mass, and then energy proportional to the square of the displacement. And one more thing, which is parallel springs, which is how it's modeled, is additive in a spring mass system. This can be shown to be constructive and destructive wave interference, coming up shortly. Now, the collective motion of granules might form wave fronts, according to Huygens principle. So let's assume that wave fronts are crossing the universe, and eventually waves from all different directions reach a center point and converge. What would happen at that point? Reflection of incoming waves produces outgoing waves, and at the same frequency now produces standing waves. And what is a standing wave? It's stored energy. It's no net propagation of energy. And what is a particle? Well, a particle is stored energy. So I think we have here our first particle defined by waves. It's going to be assigned an energy value there, just called EV. That'll be shown shortly. Now, within a standing wavelength, so standing wave with a wavelength, there are two stable nodes. Let's call that node 1 and node 2. And there are two types of particles. There's a particle and an antiparticle. And so the antiparticle would be a half wavelength on the wave separate from the particle. Now, why is that important? Because particles at half wavelengths are destructive. So if you imagine granules traveling in different directions on that wave there and colliding, the sine wave representation of that is on the right, and there's zero amplitude. Now, when they are placed at wavelengths, they will be constructive, and therefore increasing energy, and therefore increasing amplitude. That's going to be shown to be charge. Now, speaking of constructive wave interference, that's how particles can grow in mass. And let's assume here the reflection creating single fundamental particles, but now let's a little bit of energy merge them together. Now those waves converge due to constructive interference. They are pushing the displacement of other granules further and further, creating even more energy. And that energy increases actually to the 5th power, because it's not only increasing amplitude in 3 dimensions, but it's also growing the sphere as well, the number of wavelengths until the standing wave border becomes traveling waves. And that's defined in more detail in the paper in the URL below, if you want to follow that along to see how it's the 5th power. But particles are only stable at standing wave nodes, so therefore particles may quickly decay if not at stable geometries, which happens quite a bit when particles are manufactured in accelerator experiments. So to summarize this part, on spacetime and particles, particles are stored energy within the boundary of standing waves, something like that. But of course that energy does continue as it leaves. It's just traveling in form, not standing, after a certain distance. And what's cool about this is those traveling waves eventually reach another center point and become the mass of other particles, energy of other particles. So spacetime is filled with particles with waves that create particles and also cause their motion. Because if you have constructive interference, more energy, more granules reaching a particle from one side, it's going to cause a force that causes the motion of a particle. And so that's the next section we'll talk about, is space-time and forces, and how the different geometries can affect the different forces that we see. So let's clear on terminology first. So a force causes a change in motion of a particle, and of course, larger objects that we see, such as planets, gravity that you see there on the left, magnets moving, things that are magnetic, those are things that we can see, but of course all of these are made of particles. So we can break it down to forces on particles. Now, the various forces that we see are going to be described as a difference in wave type or wave form traveling in space-time. And they're going to be based on only 2 geometric ratios. One is a sphere, and one is a sphere plus cone. You can see the sphere plus cone is overlaid on top of the magnetism there, so we actually see this represented in magnets. Now, it's a geometric ratio because it's going to be compared to a plane wave versus spherical or spherical plus conical So going back to those traveling waves, planar, passing through a surface area represented by the rectangle, and then the other two geometries are the sphere and the sphere plus cone. And that's what the equations look like for surface area if you compare these as geometric ratios. Now that last one on the right, the sphere plus cone. Now if you assume that all of the variables are equal and the slant length L is pi, you get the value of the fine structure constant. Now the not actually one is going to be explained to be the electron radius, but that's a very simple way to explain that and derive the fine structure constant. Now let's start with the fundamental force. Right? Waves are traveling throughout space, and that's recognized as the magnetic constant or the electric constant with the wave speed in there. But let's go back to the sphere of Planck mass that was shown earlier. Right? Its energy is equals mc squared. You can see there. But let's take it as a force exerted on the sphere at Planck length. And what is force? It's energy over a distance. So you can see the equation there. But now let's begin applying these geometric ratios. As planar waves hit that sphere, all converge on that sphere, we're going to apply that ratio number 1 that was described earlier. All right, so Planck charge is the displacement at the electron. Now, when you apply that, you get the magnetic constant. You see they're circled in red. That's the actual value. That's without the c squared, so we put the c squared back in, and that's going to be a fundamental force. We're going to use that as the basic equation moving forward. Now, a strong force. If you were to assume that all energy reflects from there equally, as it spreads spherically now, you can measure at any point r. But it will be decreasing the force as we continue to go further out from the center. So we're going to apply a ratio here now, which is the distance r at which it will be measured. Apply that to the last one, and we're going to get an equation for the strong force. The strong force only exists within particles at standing wave nodes, as described earlier as a stable point. Beyond there, we're going to talk about the electric force in just a second and why it changes. But imagine now particles residing at those standing wave nodes creating composite particles, and that's exactly what the proton is. The proton is a composite particle. And then imagine other composite particles now merging. Same rule applies here as the nuclear force, which is really the residual of the strong force, all binding together to create the nucleus of an atom. Now back to the electric force. The electric force on particles such as the electron have spin. Now, the geometric formation of that electron might cause spin, and that spin now has not only the longitudinal wave, which was seen in the strong force, but that is actually being decreased now because its energy is also being used for spin, creating a new transverse wave. But for the electric force, we're going to focus just on the longitudinal component and the reduction of it due to spin. And that's the sphere plus cone geometry that was derived earlier for the fine structure constant. And you can see why the electron radius was used as the variables for that when it derives to the fine structure constant. Now on the far right, you see the magnetic constant, c squared, and the remaining terms in parentheses. That is the electric force. It is the exact same thing as Coulomb's equation if you were to swap out elementary charge for the Planck charge squared and fine structure constant, and also Coulomb's constant where you see the magnetic constant c squared and 4 pi. It's the exact same thing. So that is the equation for the electric force. And the electric force then is a result of traveling longitudinal waves. It's just described this way, coming into or out of the particle, but it's radiating out spherically as a longitudinal wave. Now the magnetic force. Since the electric force is the longitudinal wave, the magnetic force is a transverse wave, as it's spinning. And since it's missing longitudinal wave energy due to the conservation of energy law, we're going to apply that now as the inverse. It's just the same equation, but now with the fine structure constant in the denominator. Now this equation that you see there in the far right is not a typical one because monopoles don't really exist in nature, but that was derived to be the electron's magnetic moment known as the Bohr magneton, and there will be a URL at the end of the presentation to see how. And so this would be what the magnetic force is, a traveling transverse. It's basically a spin wave, depending on your view, what you're looking at. It looks like a transverse wave. But due to spin along the axis of rotation, you get a magnetic force. For a single particle, that's a monopole. But a dipole is more common. By pairing of particles together, such as a magnet with north and south ends. And so imagine a magnet that has that north and south, and then the electron at a distance r, and the force or effect on that electron. Now these magnets, dipoles, typically reduce their force at the cube of distance. And this is why. Using the exact same geometry again, it goes back to the sphere plus cone geometry, the variable x is now replaced with a variable distance r. And so plug that into that geometric equation and you end up with what you see there. That introduces another r in the denominator, which is inverse cube now. And this is what it looks like, the magnet forcing an electron, force decreasing at the cube of distance. And this is what we can visually see. But now let's take that down to something even smaller, such as a composite particle like the proton, which is known to contain quarks. Now if we assume two particles in alignment there in the proton, same thing as a dipole, it would have a repelling effect. Now at the same time, if there's also a longitudinal component that is attracting it, you have two forces on the electron. One that is acting as a force pushing out at the cube of distance, and one that's attractive at the square of distance, and that allows a place where you can have a stable position in orbit for the electron. And that previous equation was used to derive the Bohr radius, which is where the electron's position is in hydrogen. So a single proton, a single electron. And again, the URL to follow that path and the derivation of the Bohr radius is at the end. Now, another force we'll hit is gravity. Right? So if we assume now the particle core is spinning, of course the entire particle itself is spinning, and that was magnetism. But if you assume the very core of it is also spinning, it will have a slight reduction on the longitudinal wave energy. And that slight reduction is seen there. It's 2.4 times 10 to the minus 43, which means it's very, very slight. But it uses the same sphere plus cone geometry again, but now it just takes something at the Planck level at the core and an electron's radius, since we're going to be doing the electron's gravitational coupling constant. And that's exactly what it is relative to the electric force. So let's apply that now to the electric force equation, since we're talking about a reduction in longitudinal waves. And that's the force of gravity for an electron. Now this takes a little bit more explanation as to why that equation. So let's explain gravity here as a shading effect. So if there is more coming in than what's going out due to that spin, then it's going to produce a shading effect when you have two or more particles, such as this. But what's really cool, about that equation on the previous page, when you solve for it when these two particles are together, so that the force is at the electron's radius. So you take that r and you make it the electron's radius. You can see why it's a shading effect between two particles, because there is that spin, that geometric ratio now for two particles. And not only that, what you see circled for two particles as being the geometric ratio, but you take, it doesn't matter if it's a single particle or all the way up to Earth-sized objects. You take that inverse of what's remaining outside of the parentheses and you do the inverse of Planck length and Planck mass. And what do you get? You get the gravitational constant in both value and in units. Exactly. So gravity is a shading effect between two or more particles. And so to summarize then and tie all this back to space-time, right? In an area of space where no particles exist, there's nothing to reflect it, space-time will be evenly distributed in a structure of Planck length elements. So kind of standard grid structure. But where particles do exist, right, the reflections cause distortions in space-time and the curvature of space-time due to mass. And of course, the more mass you have there, the more that's being reflected, the more constructive ways, the larger the displacement. Therefore, the more that space-time is being curved. And for more proof, which I won't get into today, but I'll point you to the paper that you see there at the bottom. There's the URL. 15 fundamental constants are naturally derived from the Planck units discussed here and the two geometric ratios using only laws and equations from classical mechanics. Well, why is that important? Because these constants already tie to experimental evidence, such as deriving the gravitational constant G is already seen in all the calculations for gravity. For photons, the Planck constant. And so the derivation of all these constants are important to be able to tie back to experimental evidence. And so there's proof there in the paper. The question is where to go next. So future proof will be computer simulations that model particle and atom behavior using only classical mechanics.